Good morning, everybody. So in this video, we're going to solve a couple of trig equations. Now this usually comes right after you've been proving trig identities, which look almost identical to that. But in the identities, you're trying to get one side to look exactly like the other. And in these problems, we're actually trying to solve for x. We're solving for x. X is an angle. And so in the previous sections, you would not have cared what the angle was. All right, so what we're going to do first is I'm looking at this equation. Let's re-highlight this. It has a mixture of cosine and sine in it, which is going to make it hard on us. So if I look at the cosine, see how it says cosine of 2x? Well, you recently learned double angle identities, which for cosine of 2x, I wrote it to the side over here. There's three versions of cosine 2x. Now, the version I'm going to go with is this middle version because it's the only one that has sine exclusively in it. And the other side of our equation in our problem has sine, so that's how I'm picking to use that middle formula. So that's going to be 1 minus 2 sine squared of x equals 1 minus sine of x. Okay, so by picking that middle version, now I have an equation with only sine in it, which is very helpful. Now, though, I want to bring everything to one side. And don't ever do that by dividing. Do it by only adding or subtracting. Because if you start dividing in certain problems, you're going to lose some of your answers. And then I'm going to do two things at once. So I'm subtracting the 1 and adding the 2 sine squared. So I'll get 0 equals, I'm going to put this in order, so 2 sine squared of x would come first. And then I have minus sine of x. And this is actually nice. This 1 and this minus 1 subtract out, so they're gone. So now this is what I have. Now, most often what you are going to do next is factor. That's why we have 0 on one side. So we have 0 equals, I have a greatest common factor in this problem of, not the 2, I can take out a sine of x as the GCF. So I'll write over here that the GCF was sine of x. So I'm dividing both terms by sine of x. And let me move this down and show you something that students are a lot of times confused about. They think the 2 belongs with this first sine squared. The 2 is just a coefficient. What I'm doing when I take out the GCF is I'm dividing both terms by a sine of x. Now when you divide, you subtract exponents. So what it's doing in this first term is taking away the squared and making it to the first power. So the sine of x divides out and leaves you with just 2 sine to the first power of x. And then in the second term, the sines divide out and give you 1. Don't think that that is 0. It's minus 1. Then I use the zero product property, so I set each of my factors equal to 0, like this. Okay, and then with this second one, I need to do a little bit more work. Add 1, and then I'll have to divide by 2. I'm just going to do this all at once. So I get sine of x equals 1/2. And in this one, I have sine of x equals 0. Now this is where we need to think of the unit circle. So sine of x equals 0. That's going to be at one of the 4 quadrantal points. If we just put in the coordinates, that'll help you see it, I think. Sine, remember, is the y-coordinate. So the two places where the y-coordinate is 0 is here and here. And those two angles would be 0 radians, and over here it's pi radians. So this first sine of x equals 0 part gives you that x would be 0 and x equals pi. So those are two solutions. Now I'm going to work through sine of x equals 1/2. So I'll highlight it. So I'm doing this now, and I'll use my same xy coordinate plane. So sine of x equals 1/2, that could be either in the first quadrant or in the second quadrant, because that's where sine is positive. I'm just going to get rid of some of these numbers to make a little more room. And we know that sine is opposite over hypotenuse, so I could label my triangles like this: opposite over hypotenuse. Everything is in relationship to the reference angle. And then you should know that this is a 30, 60, 90 triangle with this side, this missing side would be rad 3. And on that triangle it would be negative rad 3. But the important thing is that the angle that is the reference angle would be 30 degrees because it's across from 1. Now 30 degrees, this is all stuff that you probably know, but 30 degrees is the same as pi over 6. So one of our answers for this blue highlighted portion is that x equals pi over 6. And then the one in the second quadrant, the answer is going to be 5 pi over 6. And the easiest way that I tell students to think of that is this pi over here, this pi right here, is the same as 6/6 pi. And so if you're stopping just short of that, which you are when you get to right here, that causes it to be 5 pi over 6. And so those would be the other two answers. So you get a total of 4 answers for that problem. Now I've written out one more. This one's a little bit different. The only thing in this problem is a sine of 2x. So I'm not going to use a formula to change that at all, because if I did, if you remember back, the sine of 2x identity or formula is 2 sine of x cosine of x, which would cause more trig functions to appear in our problem. It would make a sine and a cosine show up. So I don't really want to do that. I'm just going to leave this the way it is. I'm going to divide by that 2 on both sides. So I get sine of 2x equals 1/2. Okay, now I'm just going to ignore the fact that this is a 2x for a minute. Let's call it something else completely different, like if I just say the sine of theta equals 1/2. Okay, and let's think that through. It's actually the same as the problem that we just did. Sine is positive in the first quadrant and in the second, and it's opposite over hypotenuse. So that would be the setup of the triangles. That means that the missing side is rad 3. And that means that our reference angle, again, is 30, which is the same as pi over 6. And remember, we said this other answer then would be 5 pi over 6. So far I get theta equals pi over 6 and 5 pi over 6. But we weren't really solving for theta, we were solving for 2x. So far I have 2x equals pi over 6 and 5 pi over 6. Because 2x and theta were the same thing. I just let theta replace the 2x. So they're just interchangeable. Now before we finish off the answers for x, here's what I tell students to do. Look over at the original interval. That was the interval that x had to stay on. But in the problem, there's a 2x. So what I would do is I'd take this interval, give myself just a little more room, and since it was a 2x in this problem, I would be multiplying every part of this interval times 2. So 2x can stay greater than or equal to 0 still, and less than 4 pi. That means that you can actually twist around the circle more than once. So we had our first answer here, which was pi over 6. Then we had another one here, which was the 5 pi over 6. But now, if I can keep going until 4 pi, I can go all the way back around again to that answer. Now this is how I think this through. We're dealing with a reference angle of pi over 6. So think of this as 6 pi. Directly over here would be 12/6 pi. So if I'm ending just past the 12/6, that's going to make that a total of 13/6 pi. Okay, now think if you kept going around, we need the other answer that would be located here. After 12/6, that would bump this up to a total of 18/6, because everything is just 6/6 apart. So by the time I get directly over to the left, it would be 18/6. So this answer right here in the second quadrant, which is just before the 18/6, would have to be 17/6. And then I cannot keep going because the interval said that you can only go up to 4 pi. So if I keep swinging around, I'm going to get to 4 pi right here before I come back to any more answers. So I'm done writing down my answers. But the last thing is that these are the 2x answers. So to get just the answers for x, I have to divide every single answer by 2. And when you do that, it's the same as multiplying by 1/2. So it basically just turns all the denominators into 12s, because pi over 6 times 1/2, just think about that to the side here, that's pi over 12. And if I keep doing that with every single fraction, it's just going to be the same thing. So 5 pi over 12, 13 pi over 12, and finally 17 pi over 12. And that's it. Now, in a problem where you have 2 solutions, which is the normal type, if you have a 2x, it will double the amount of solutions, so you'll have 4. Now, of course, there's exceptions to that rule because some original problems don't have 2 solutions. They might only have 1. And then if you have a 2x, it would still double the amount of answers. So if you had 1 answer before, you'd have 2 answers in the end. But with this problem, we had 2 answers originally with the theta, and then because it was a 2x, we had double the amount, so we had 4 solutions. So hopefully that will help.